I will go on and read Andrea's email first, and then I'll do the self-introduction and then my lecture. Hi all, I am writing you because due to some family issues, unfortunately, I couldn't join the event Rese MEETUP in Bratislava. I want to apologize first with Jan, then with the other speakers and conference participants. As you maybe know, I don't consider myself an expert about swarm systems and behavior, but I'm really interested in it, since I consider the swarm as a fundamental actor in the design and building process of tomorrow, if not already now. 2 years ago, during a Code8 meeting, we decided to give high priority to all the projects that give us the chance at least to prototype our design, if not to build or 3D print at one-to-one scale. The fabrication process is fundamental to test our design and have all the fabrication feedbacks that are essential to develop new kind of design sensibilities and to improve, in a feedback loop, the design of our digital processes. Without fabrication, we can't discover first the critical issues and then the emergent features that are in some way what as Code8 we are looking for in our informed matter research. In the last years, we had also the chance to work with some companies that are trying to 3D print at architectural scale using big 3D printers, such as D-Shape and Wasp. I consider the idea to scale up the tools along with the model size and all vision and all the use of new technology, and we told those companies. To build to the architectural scales, like a big one, I consider the swarm robotics the only way, because swarms could incorporate a plurality of actors and speciation of tasks. And since architectures not just build a shell, but incorporate also different features and function in the building process, the ability to perform different tasks at the same time, but many actors, is essential. Lately, I had also the chance, or better, I thought to have the chance to play with robots and start to learn a little bit of robotics. This experience gives me the chance to think about the relationship between the code, the program behavior, and the robot, the body, to explore the surrounding world, able to sense and act on it. The embodiment of a behavior is something really close to some of my too many interests. Cyborgization and the umwelt. Build a robot is not just a technical issue, but it's a process to define a sort of specific umwelt of the infinite possible, and talking about swarm robotics means to define a swarm umwelt, a really fascinating topic to me that I would really go deep in and discuss. I wish you a great event and conference, but I'm sure it's going to be, since Jan is a very talented organizer, computational designer and thinker. You don't need any wish in that sense, and the event, I'm sure, is going to be great. I want to underline what is more important to me about this event. The way Jan decided to do a meeting between several expert speakers, giving the chance to talk and exchange experiences in order to improve the quality of our work in such a pleasant, informal way and without any academic support, is something really relevant and rare. And sincerely, I'm really sad to don't have the chance to be part of it. I would really like to meet and talk with the speakers that are already friends, and I would even more talk with the speakers that I still don't know. Have a great time. Again, a big thank you to Jan and the invitation, and a big ciao to all. That is on behalf of Andrea. All right. I am Alessio Erioli. I'm one of the other co-founders of Computational Design Italy, along with Andrea and with Davide Del Giudice, which is currently employed as an architect at Zahadid in London. When we started thinking about working together, we met online, basically publishing on each other's blog and starting to comment, and then we met back in 2008, and in 2009 we decided to start Code8. We are not really a studio, not really, I don't know if we are a collective or something. We consider ourselves as a sort of a hub, a catalyzer in what is a process of design and consulting. We do several things besides our work and research. We are interested in improving or having our say into education, in doing networking, because we gather a lot of knowledge from people who have decided also to share and network not only their own contacts, but their own knowledge, their own competence, and we feel it's not just fair, but it's a good way of improving the overall ecosystem of work doing the same. And all of those things are inevitably connected. Whenever we do something in research, it has echoes in education, in our work, in the way we do networking. So all of these activities matter to us. And the way we organize them is a very open and heterogeneous, which is we organize teams around topics. We are interested in a certain topic, and we'll look and reach for people that might be interested, and then we aggregate the team in that way, which has also its downsides, because you have to get the availability or meet around the availability of each and every one. Today, what I was interested into talking about was an idea of continuous tectonics, which is the thing I also put in the opening slide. But first of all, I have to go through a few introductory concepts just to share a little bit what is our vision and our take on what is the contemporary impact, especially of computation in several disciplines, which starts with architecture and design, and then they expand further, also redefining what architecture is and what design is. First of all, is an idea that is coming back from afar, which is the idea of craft, which is something that maybe has been cut away from the industrialization of processes, and that is coming back, but in a different way. Ruskin was defining that the activity of an artisan like shaping with his hands the free flow of his mind. But I think that there is the return of craft in terms of a computational craft, but it's not anymore tied to a human or a handwork anymore. It's linked with something different, but still has something in common with that activity. It's something that joins together thought and action. So it's thought through action, or thought that becomes action. In a way, I define craft as the accumulation of knowledge that sublimates into a sensibility. When something becomes intuitive, it becomes a sort of a craft. It's all the knowledge that you accumulate and you express through an activity intuitively. And that for us is something that is expressed right now through computation. Right now we're doing it through coding, so there is some sort of computational craft done through coding. That's something that allows us to use computation not just as a tool. In our mind, it's a design medium, something that needs to be navigated, that needs to be explored. And especially one of the main things, it's about designing behaviors. And this especially is something, build our own tools, build our own machines. But why build our own tools? Well, build our own machines. It's exactly to take a step beyond what is our human condition, our human thinking. Like building machine through the code enables an inhuman factor in the design. The more intelligent the system we build, the more inhuman they tend to get. And we are interested exactly into that, not just trying to bring them to a human perspective, but resisting this impulse of humanizing things and letting the inhuman penetrate and have its own voice in the design and start an interaction with that. And on that, sometimes when you write an algorithm, you cannot trace what the algorithm is going to do just by reading it. You have to see it in action. You have to see what it does, and you have to understand what it does. One of the things that I'm going to show first was one of the experiments I was doing while teaching the AA visiting school last year in Dubai. And it was a sort of growth by modular growth, sort of an aperiodic modularity, which is we have a single module because we wanted to go into the production of this single module, single shape, and have this repeating, but trying to produce variety, as much variety as possible, but without having these modules, touch each other or compenetrate each other. So it was a sort of study with growth rules and avoiding certain obstacles, certain things. So it's programming growth behaviors around it. And you have this sort of condition. Of course, there's a lot of abstraction still in this part because we weren't able to start coding inside some sort of structural behavior, some more directed growth, but still, it was an interesting way of trying to make one step beyond what is the easy imagery or the straightforward implementation of modularity in a way. But I have to say that personally I'm more interested into something that goes even beyond modularity. And I'm interested into behaviors, complex behaviors. And of course, one of the first sources of this thing is looking at the biological world, looking at the processes through the lens of biomimetic approach, but not in search of shapes or forms, in search of principles that can be abstracted and reapplied for their capacity to produce complexity, for the capacity to produce complex outcomes out of very simple behavior. And on that, I will go on with a very interesting quote by Daniel Dennett, which is a philosopher which is rereading Darwin. And it's interesting, the take of Daniel Dennett. It's interesting for its potential application in a design approach. And it says that, well, it's hard to believe that something as mindless and mechanical as an algorithm could produce such wonderful things. He refers to nature, of course, but he could apply that to design. No matter how impressive the products of an algorithm, the underlying process always consists of nothing but a set of individually mindless steps, succeeding each other without the help of intelligent supervision. They are automatic by definition, the workings of an automaton. Or in short, what he says is, he himself says that synthesizing Darwin's vision is about design. Give me order and time, I will give you design. Of course, it's not just like that, because design shifts and the control shift, but I will more on that later. And this interest also arrived into the field of art when a group of people in the 60s, specifically Sol Levitt, Werner Molnar, and others, starts getting interested into what a computer could do. And they start discussing also another very interesting topic, which is the role of the author, who is the author. And so Sol Levitt put this in his paragraph on conceptual art in 1967. So the idea becomes a machine that makes the art. And other artists, such as Richard Serra, they work building machines. A lot of artists worked through the centuries building machines to, let's say, resist the easy imagery, the easy implementation. Caravaggio built a machine to create the perception of a certain kind of lightning. Other artists build their own machines. And the computer becomes another very interesting, let's say, maybe a meta machine, a machine to build other machines. So the idea becomes a machine, but don't think a machine as something mechanical, but in an abstract way, like a set of operations, a series of operations. That's already an abstract machine. And then you can implement those operations in different mediums, and then you have this different implementation. So to go on and paragraph what Sol Levitt was doing to what we are, or trying to define a little better what we are trying to do, is to have the code design machine and then grow the architecture. So into this whole available framework of self-organizing systems, of emergent processes, nonlinear processes, the thing about design is that it is the amount of decision that you put and the pattern of how these decisions are scattered through the systems, and how you make use of this system, how you let them go or decide to direct them, the constraints that you put, the rules. There's a very elegant synthesis to that Steven Shaviro did. And he claims for an aesthetic of decision in a framework of self-organization and complex adaptive system. And I find this sentence a very elegant synthesis of the kind of approach. Thinking about aesthetics is the same way. I won't go and try to define aesthetics right now because it's not my role right here now. But to give an understanding of what I mean, it's as there is an aesthetic of language or an aesthetic of music, it's not something just visual, but it's a way by which you organized a medium or language to deliver some content. So the same idea, for example, of the Divine Comedy written by Dante gets a certain aesthetic of language. If you take another writer and you tell him to write down the same idea, then the content is even delivered differently. But there are two different aesthetic of language at play. So to go on and go to the topic at hand, the idea was to me to trying to overcome this distinction between the phase of construction, the definition of construction as a process and the construction as an object. Right now there are like two sides of a coin that are mutually exclusive. When you have the construction process, you still don't have the object, and when the construction process ends and you have the object, the process is cut away. But this doesn't happen in the biological systems, in a lot of systems that we've seen also in examples yesterday, like collective construction by insects. So the construction is a perpetual process that goes on forever, and the object, the agent constructor, and the process are woven together, and you cannot separate them and make a distinction. So the continuity and the tectonics, continuity is intended in this twofold way, like a perpetual process in time, but also in the way in which relations are defining and letting the objects and the beings emerge from the unfolding of this relation in space and time. And tectonics, as for me, it's defined as the universe or the sphere in which you start establishing relation, or the relation are starting to establish between the morphological organization and internal logic of operation. If you want two terms mutuated from biology, it's the relation between morphology and physiology. So how a building or an architecture is formally organized, and how the relation between this formal organization and the internal logic of operation are starting to unfold, and how they decide all the subsequent individuation of the whole and the individuation of the parts. What is the system, what are the parts, and so on. And this has to do with a concept that I came across recently that is very interesting. It was formulated first by Luciana Parisi, as far as I know, in a book which is very interesting, Contagious Architecture, which I'm still in progress of reading, but it's full of very interesting theoretical ideas. And it has to do with the mereology, which is the part to parts and part to whole relations, and also with the topology that has to do with continuity, connection, and the boundaries, definition of boundaries. So it's not just how the parts are related between themselves or with the system, but how the parts are individuated, or like how you define them as parts as respect to the whole and stuff. There's a very interesting definition about the semi-open parts, which means the idea is that the environment as sum of all possible environments is a random infinite. It's made of infinites, and the parts are a finite quantity, but they are able to process somehow this infinite from the environment. Then inevitably they are kind of absorb it and let some of the randomness of the environment filter through. Usually our understanding, or let's say not our, but the traditional understanding of mereology has a lot to do with finality, especially from the modern, but even earlier on. But we are used to this industrial model of each part with the finality, the roof, the slab, the wall, the pillar, and so on. And it's finality in its essence, in which every element is perfectly individuated prior to be put in the system or be put in action, and everything has a specific finality and a specific task in the system. And that is at this opposite. You see on the left this exact concept. This is a diagram which is recalled by Deleuze of the chess and the Go, in which the chess is the finality with all the elements as actors with a predefined role from the beginning, and this goes back also to Trubius and to Alberti, where everything should have this own perfect, let's say, role and individuation, as opposed to the Go, where each pebble is self-similar, but it changes its role according to the position in space and to the mutual relation with the other. On the opposite, you have the King's College Chapel, where this rib element continuously goes from or shifts from surface to structure to ornament to a fan configuration, and then it makes the capital, and then it makes the pillar, but there is no sharp distinction in the way they start going at it. So the thing is that the parts or the roles that the traditional tectonics, for instance, from Semper goes from the massing to the surface to the ornament, they should not be read into a construction more as a sort of fixed object, but more as behavior distributed through the artifact. So you have structural behavior, so you read things that concur into defining what the structural behavior is, or the surface behavior, or massing behavior. And for example, in this, one of the experiments from Frei Otto, for a tower model, everything started from similar, identical strands of wool. Then they are put into water to simulate the action of forces, and then they shift into a system in which you don't have the individual parts anymore. They're not anymore discernible into the system. But there's a irreversible change in the system, and then you have all these singularities, and you have a transition between singularities, like a heterogeneous path system full of singularities. And the other thing is that all this configuration, like in this skeleton of a saguaro cactus, they operate according to an internal logic, but the determination, their finality is open. It's not determined prior to the action of construction. So it's a condition which Lars Prybeck refers to the inexact, which means exactly rigorous in its logic, but open in its determinacy. And it defines another condition which is very important, which is the condition of vagueness, which is not lack of logic, but exactly lack of determinacy. And the logic of vagueness is exactly what constitutes the relations. So the relation as defined in their internal dynamics, but their results can be open. It was something that we tried to explore through material implementation in a thesis project I advised. This is the thesis project by Gianluca Tabellini, and we tried to make a sort of directed growth of mycelium and through the decision in the basic structure, and see what the growth of an organism that is able to make a very, very complex configuration could give, or the suggestion that could be given in terms of how the material organizes itself and how they could be eventually translated to a larger scale, maybe not in the same material, but also trying to grow up with the material itself. So this was one of the latest results, a self-standing column of about 35 centimeters, grown from the straw, and the mycelium grows and create also a self-stable structure. And in that, the use of the material is something that, or the design opportunities that are there in between algorithm, simulation, and fabrication are something that is very interesting for us to explore. We don't want to go into that. This is an art piece by Josef Kosuth. It's 1 and 3 chairs with the same object. The chair is presented in 3 different medium, like the chair itself, a picture, and a description, which is usually the condition of many situations in which the tools are used. Which you have the object, then you have the render, then you have the description, but they are the amount of information exactly the same, just changes the medium. But we believe that in the transitions between all these phases, there are design opportunities that might be explored. This is something that I also tried to explore in the woven Tectonics, which was my tutoring unit at the visiting school in the year before the one you saw earlier. We wanted to go with the Tectonics with this tabletop robot that was built by Suryansh Chandra. And the idea was to try to embed into this woven Tectonic as many features as possible, especially in this case, structural surface and ornament specifically. So these were some of the final results of the unit. And it's also this course of embedding the logics into the Tectonic. For instance, I really like very much this example from a traditional construction of the Musgum huts, where the element that you see on the right, it's a multi-purpose element, a multifunctional element. It has a multiple performance. Structural stiffness, it helps draining water. It has an ornament and a communication function. Then you identify which family this hut is from. But most of all, it's the construction device itself. It's the place where they place their feet while the construction grows up. So it has no, let's say, scaffold. It is the scaffold, but it is also the element. So it has a function that it has to do with the dynamic of construction. And also it's related to another factor, which is the anatomy of the constructor agent. The pace and the distance in between the elements is connected to the anatomy of the leg and how you climb things. And it's pretty much also something that it exists in insects and nature that build and also use other insects to build. So this is a weaver ant that is squeezing another tiny little element to get this glue and get the nest done by gluing together leaves. And there's this beautiful material expression also in between. So in the basic, let's say, diagram that we consider for the thing is it goes through this cycle, this loop in between the architectural perturbation and this recruitment, structural alteration, and you make an alteration in the architect, and then the atmosphere changes, and then this loop goes on. And of course, since we were talking also about swarm logic, there are the 2 logics at work, the Reynolds logic and the Stigmergy logic, as implemented by Jeff Jones. I want to go straight to the examples because I'm kind of rushing up with time. I will skip one of the examples. One of the things that we are interesting about right now is exactly the material feedback in the robotic fabrication, and we are exploring that in one of our ongoing research, which is this digital touring, which is a partnership of different entities in us and Coma Robotics and several other actors. So the idea was to not design shapes, but drive the robot's behavior, the robot trajectories, and simulate that, but not trying to reproduce exactly this result. This is just to test if we have problems clashing and stuff, because we don't have continuous access to the robot, so we prefer to do some simulation. But what we really are going for is trying to understand the potential role in terms of performance and aesthetics altogether of when you let the material go and let it have its say in the performance and in the process. So this sort of effects that are normally considered as something defective because it's not the exact image of the process, but this was for us very important. So very quickly some of the results. And I will try to conclude with one last example, which is another thesis project that has to do with more with the topic of continuous tectonics, which is this thesis project by Michele Semeghini. It's called Swarm Constructability. So the idea was to exactly try to go for a swarm of robots, but one of the first, let's say, bottlenecks was, okay, we have to feed them autonomously, we have to give them energy. So we need to find a material that requires the least possible energy to make the position so that we can use all the energy for the robot locomotion. So we had two alternatives. One is polycaprolactone, the other was sodium 3-acetate. And we went for the second one because it works at room temperature, but it turned out to be very unstable. So in future implementation, we are trying to improve further this aspect. And also, this went through the custom design of the whole unit, the whole robot. The initial ambition was to build several of those units, like 10 or 20, but budget. And we ended up with 4 units. But as a proof of, it turned out to be more a proof of concept than a real system, but still it was interesting because we could learn a lot from the whole thing, especially in terms of defining the robot behavior, because there was no information transmission. We wanted to keep the system as stupid as possible. So very, very simple instruction, and see what we could extract from the pure interaction of individual autonomous behavior. So we coded every behavior we needed in the robot, and through simulation and work in the real world environment, and see what we could have as a feedback. So all the chemiotaxic stigmergy and how you go solving the problem of things that are moving and are depositing something, and you have to avoid them hurting it again and destroying everything. So to solve this, we decided to turn the thing inside out. So the robot is hanging up through magnetic wheels, and it's depositing downward. And it's through a LED light and a light-sensitive paint. It leaves a trace, and the other robot can follow up. So this is like the layering of the system. This was the first deposition test. Actually, Stuart went for something quite similar in terms of technique. It's dripping and it's solidifying quite quickly. But we didn't we chose to find something that didn't require heating for the whole process, just to save energy. But as you can see, it takes forever to do something. So this was the problem with the material, but it was too late to try to switch to a new design, because there are always difficulties in developing things. And this is how the stigmergic operation was performed. So there is one robot that is depositing a light streak by a high intensity LED light, and each robot has this LED light in the back and the light sensor in front. So one is depositing the light and the other is it's detecting and following. But just by tracing these 3 parts in the LED, so according to where the intensity is higher, it steers one way or another. And sometimes in more complicated situation, it might get lost, which is a lot of learning again that we could do on that. And so it was like the big simulation, but what we realized is that there is a huge scale problem here. The dripping is a very, very tiny particle, deposited by a huge unit. So we, for sure, if we going on with this exploration, we need to find a way of reversing as much as possible this ratio between the size of the agent and the size of the built stuff. And it turned out to be a good proof of concept anyway, because then we made some more extended simulation. So part of the designer decision is not driving the robot, but using this predefined maps, or pheromonic maps that we could impose by, doing some light streaking or projecting a light pattern into the environment, having the robot trying to solve that and arrange them. So trying to tease some building behavior, like building cavities or building dendritic structure or building pillars. So trying to tease out all this behavior while the process is going. And these are some of the extended simulation result that we did. It was it's still a work in progress, but there's an interesting thing going on, and we'll for sure try to go on and try to tease as much intelligent organization as possible with the stupidest robots possible. So that's it. Thanks for... Okay. Well, for sure, I would like to go on with the swarm robotics. Is our interest as not just mine, but Andreas as well, as you heard from the letter. So trying to move on to the swarm robotics, but it takes right now it takes to us a bit of a long time, because we have to gather the resources to start doing these experiments. But for sure, it goes in that direction, and it takes several factors. One is programming behavior, understanding the anatomy of the agents. So right now, even using the large-scale robotic arm, it's an interesting learning path to understand and to develop further. And also through the informed matter research series, we are trying to understand how to how to incorporate material behavior as a design factor. So we are trying to progress in that direction. Currently, let's say the last 3 or 4 months have been quite hectic. So we have to put things a little bit on hold, but our intention, our direction is in that way. It's quite elementary, because you have this light sensor. If that is the question, technically, you have this light sensor, which is a row of sensors, and then you have data from each of the sensor in the row. So you know the position, and you know which one is left or which one is right. So according to, let's say, you know the size of it, and you actually have a vector pointing, and you establish which has the largest intensity, and then you find the direction, and you calculate the steering angle, and you calculate the code that you have to give to the stepper motors to make it turn. No, they are quite antisocial, sociopathic robots. Besides this, they just read through the environment. They don't interact directly to each other. Also because that was another thing we decided to avoid, because then you had to input sort of a wireless transmitter, which meant more energy spent for that. So we tried to start from the most basic unit possible to give all the energy into locomotion automation. We wanted the robot to go on as much as possible. Yeah, they tend to go where the streak is the brightest. So they choose a center way. They get lost sometimes, but tendentially it works as a stigmergic strategy, because they tend to follow the brightest streak. So they tend to reinforce the strongest pattern in their own way. But of course, there are a lot of implementation problems, especially with the scale of locomotion, and also that we cannot control very well the evaporation ratio. So we have to scale everything to that. That was the constraint. No, actually it was the other way around. We built the robots and we tried to implement the physical constraints into the extended simulation. So one of the reasons why we wanted to go for the robots and build them first was the limit of the current simulation with agent systems. First of all, that mostly they are represented as dots, but they have a body. So there are all these difficulties of implementation, and we tried to bring this back to the simulation. The other thing is that the simulation have a computational bottleneck, which means the interaction are not simultaneous. They are almost like that, but they are still serial because you go through an array and you go from first to last all the time. While in the real world, they are really simultaneous. So there is this difference factor, and we wanted to see how much faithful the simulation was going to be with respect to the thing. This, of course, is the part that we couldn't translate back into the simulation because we need like parallel computing, real parallel computing to do that. But we tried to feed back the physical constraint back into the simulation as much as possible. It's a very interesting question because it's actually we would need to start doing things at larger and larger scale and start having even like building up. I think this framework still needs to build up as much as we progress. Like how do we evaluate? Partly I was talking about it in the more, let's say, theoretical part, which is understanding where are the behaviors, the tectonic behaviors distributed, like what is concurring to make the structural behavior, what is concurring to behaving as a surface, or the energy distribution behavior, what are the parts that are concurring to that, and how can we understand it and be able not to predict them, but to drive the way they are expressed, or where they are expressed. Also, the other thing is that the ambition is not to have this thing limited to just the construction phase, but the fact that this agents constructor, which are right now mechanical robots, but the other part is that the possibility to also work with synthetic biology and have biological machines constructing. It's also that these constructors are an inextricable part of the building, which means they are able, the construction never ends. I mean, there will be a huge, let's say, expansion phase, but then there's also some of the performance is going to be dynamic. Thermal regulation or adaptation to seasonal change means that some parts of the building are continuously built, some other can be destroyed and recycled and rebuilt. So it is pretty much what happens with the termite mounds. The termites are continuously building new holes, new tunnels, and let's say closing other ones to maintain homeostatic stability of the energy inside. So the idea is exactly that these things in their, let's say, final ambition are not just the constructor and then they go away. They are the project in a sense.
Thank you, Alessio.
Thank you for inviting me and all.